this evening I wanted to talk about image processing using Go, specifically about using just the Go standard library. I'm not particularly being masochistic here, but I'm just trying to show what are the possibilities you can actually do with the Go standard library, which is a lot, to be honest. Of course, if you want to do a lot more extensive stuff, normally you would try to use a maybe a more performant library that's very specific to what you want to do. But the reality is you can actually do quite a lot of stuff already with the Go standard library. So if you don't have a lot of requirements and you don't want to add on to another package that you are dependent on, then give the Go standard library a spin. I'll talk a little bit about that today. So before I start the presentation, let me do a quick pitch here on the Go recipes site. So basically the materials I have here today, they are based on the book that I'll be writing, or I'm currently writing for O'Reilly, called the Go Cookbook, and a lot of the things that I'm writing will be coming up from the gorecipes.dev website. So if you have some time, please go check it out. All right, so let me get on with the presentation, and it will be a presentation. I could run some code as well, except that switching between the slides and the terminal, and also that I don't have all the code in one piece to show everyone. So I won't show that today. But of course, if you ask, I could show something, except that it would not be exactly running the way that I show in the slides. Anyway, so let me start. Image processing in Go. Here, what I'm talking about is image processing for raster images. The algorithms here and the mechanics are actually quite simple, right? It might sound a bit daunting, say, hey, this is image processing, so it's quite difficult and things like that. But actually, the basic principles are quite simple, and you probably have learned it in your computer graphics in university. So the algorithms are basically just that, not that difficult. And if you see some of the things I do today, you will realize that Go makes it relatively easy, and sometimes can be pretty fast as well. There are, of course, a lot of other Go packages that you can use. But if you just want to stick with the standard library, you can do a lot already. So, like I said, this presentation is based on the materials I'm writing for my new O'Reilly book. It's coming out sometime either next year or sometime really early 2023. Okay, so what is the package that you want to use for image processing in Go? So no surprises here. This is the image package. And the main interface is image.image. This is not very surprising. It's an interface though. So you might want to be careful. This is not an actual implementation. The interface has three main functions, methods. The one that you probably use the most is at. At basically gives you the pixel at a specific XY location. And if you look here on the screen, color.color is basically the pixel. Okay, so this is the main interface. This is something that you'll be using the most often if you are going to do anything with image processing with the Go standard library. The other structs and interfaces you would use rectangle. Basically, it's a rectangle. It has a min and max point, which are the 2 points that define the upper left and the lower right of the rectangle. Point, again, it's very straightforward. It's basically a point on a 2D, two-dimensional, flat kind of interface, and that's really the image interface that you will see. Then finally, this is the pixel. Pixel color here is an interface, and it has only one method, which is RGBA, which gives you the red, green, blue, and alpha values, right, which are the unsigned integer, unsigned integers. Okay, so RGB and A. Right, because I said earlier, image is an interface, and there are a number of structs that implement it. So these are just an example of some of the structs. The one that I would be talking most on today, in fact, the one that I'll be only talking about today is the NRGBA. So this is the non-composited image that I'm talking about. RGBA is the RGB with the alpha, and this is a composited image. Then CYMK is another scheme, and so on and so forth, right? Gray is grayscale. You would normally be using the implementations rather than the interface. So just be a little bit careful of that. Okay, so this struct has a certain values that I'll explain. But the one that is most important for us is really this one, pix. Pix is an array, it's a byte array. Like unsigned integer 8 is basically a byte that represents pixels all laid up in a single row. So if you have a pixel that's represented in RGB and A, so basically you have RGBA, 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 and so on and so forth, right, until the end of your image. Stride is the pick stride in bytes between vertically adjacent pixels. So basically the stride between the two pixels, and the rect here represents the size of the image. Okay, so that's it. Really, that's all there is that you need to know about the basics of the image package, and you can jump straight into doing your image processing. Before we do any image processing, then one of the first things you want to do is really load an image. You want to load up an image and work on it, right? So how do you load it up? So first thing first, you need to register the format by initializing the formats package. If you are just loading and you're not doing anything else, you can just import underscore. Then, because if you import something and you don't really use it directly, then when you do go format, you'll be removed, right? So, or you will throw an error. So if you are not using the format package directly, then you need to put an underscore. And you need to put an underscore because it allows you to initialize, or rather call the init function within the package, and that allows you to use the PNG to do decoding, right, when you load the image. Okay, so this is the load function that allows you to load a file. Basically, that's a PNG file here that we want to load up, and it will return image.nrgba. Okay, so the usual one is you open up the image file, the top part here. It's basically just opening up the file, and then you call image.decode with the file name. Oh, sorry, with the file, and you'll be returned with an img, or rather the image variable. And this image variable is an interface, right? Because whatever is returned to you is image.image. If you want to return it in an actual implementation, then you need to do a type assert. So here we do a type assert to image nrgba, and then you can return it. And with that image, you can do whatever you want to do next, right? So that's basic loading. And of course, once you're done with everything, then you want to save the image back to file. So how do you do that? This is the code for that. And again, the first part of it, it's nothing special. This is about creating a new file, a blank new file. And then here, remember, now you actually need to use the package for the specific package that you want. Let's say you want to save this as PNG, then you need to use a png.encode function. You pass it the file that you just created here. And what you need to do is also pass it you need to pass it an image.image, because the encode method needs an image strut. But obviously, what you have here is image.nrgba. What you need to do here is call image.subimage. This is a method within the nrgba strut that you can get a part of the image, but here we pass on the entire size of the image. So basically, this is the entire image. and this will return image.image, which you can use for the encoding. Right, and finally, when this is done, you'll be saved to the file, and then you would have the PNG file. Right. So the load and the save, basically, they are just reverse of each other. Nothing fantastic, nothing like very fanciful, quite straightforward. Right. Now I'll talk a little bit here to show you how you can actually use the image package to create a random image. And here there is nothing else except with image, and then you provide all the values within the image, and that will create a random image. How do I do that? So this random image here, basically here I create a pix, which is a byte array, okay? And then what I do is I call ren.read, and this will populate the pix byte array. With this pix byte array, I can create an image.nrgba, pass it into pix variable. You put in a stride, you put in the size, and you're done. Basically, this will actually create an image.nrgba. Okay. Once this is returned, you can call save, and it will do the encoding, and it will be saved as a PNG file. So what do I mean by a random image here? So you might think that, hey, would it just simply go out to some website, Facebook, Flickr, whatever, and grab an image and put it here? No, basically what I mean by random image is random pixel, right? So I will randomly put a pixel, and then you will create this image. So this is an actual image. I've enlarged it because it was the image that I created here is actually just 100 by 100 pixels. But you can imagine it can be a lot larger. Okay, so a random image. How useful is a random image? Well, mostly it's not very useful. So what can you do? Right? How do you actually do more image processing? Let me jump into the next section, which is talking about representing an image with a grid and why we want to do that. So you saw what I did earlier on. Basically, I generated an image using a byte array by putting pixels into the byte array. But obviously, it's not the best way to do processing, because the way to visualize it is not the best. The more natural way to do this is to represent it in a grid of pixels. Basically, it's a two-dimensional grid of pixels, right? That's basically a raster image. You know, this allows us to manipulate the image a lot more intuitively. And then, of course, all the algorithms that you learn from school, you can actually apply here as well, right? So how do you represent a pixel? So color.color is the interface that represents a pixel, and the specific pixel, the actual implementation is color.nrgba, color.rgba, and so on and so forth, right? All those others that you saw earlier on. The best way to really understand a little bit more about this is get into the image package or the color package, sub package, and then you will see what I mean in there. So essentially what I want to do here is to convert a byte array into a grid of pixels, right? So with this, I want to go back to the two functions that I talked about earlier on. First is the load function. So I want to make it such that instead of returning an image.nrgba, I want to return a two-dimensional array of pixels, right? So color.color is a pixel, so it's a two-dimensional array of color.color, which is what I'm returning. So the code, it's the same as previously. The only thing I added on is an extension of this. So first, I would find out the size of the grid that I want to create. So this image.bounds.size, this will gives me the basically a rectangle of the image, right? And for here, I would create columns of pixels, and after that, I would append it to another array, and that ends up being a grid. Okay, so again, nothing rocket science here. So this is just iterating through the pixels, and then I append it and make it into a two-dimensional array. Of course, with loading, then I need to talk about saving. Again, saving is not difficult. So first of all, I need to create a rect. First I need to create an image of the correct size of the rect size here. Then the rect size is basically the size of the grid here, right? And then from then on, I use image.set, and this will set the new image that I created at the different X and Y positions with the correct pixel. And after that, I encode the image into file. Right. So load and save, but this time as a grid of pixels. Okay, so with that in place, we can proceed to do a lot more different types of image processing. Let me start off first with the first and the easiest probably, which is to flip the image. Okay, so what we want to do is flip the image upside down, and let's take a look at the code. Pretty straightforward. Yeah, I won't even like go through the code at all here. Basically, I do 2 iterations for X, for Y, and then I just flip the X and Y. Okay, or Y and Z. Sorry, the Y and Z here, which is basically the top and the bottom pixels. And once I flip the top and bottom pixels, this is what you see. Right, I'm using an image of this bird. This is a parrot, a very colorful parrot from Australia. And basically, I flip the file by exchanging this pixel with this pixel and this pixel with this pixel all the way. Yeah, then this one with this one, this one with this one, and so on and so forth. And you end up with this once you save the file. Okay, that's pretty straightforward, right? It looks so simple, and it is really that simple. You don't really need to have a very complicated algorithms, at least not yet. Let me get into the next one, which is making an image grayscale. Okay, so what is grayscale? Grayscale is basically a picture that shows different shades of gray according to the light intensity. Yeah. So instead of having the color, basically the different shades of gray according to the intensity of the light that's according to the pixel. Okay, so to create the grayscale image from color, what we need to do is just calculate the relative luminance of each pixel from the RGB values. Remember earlier on we had the RGB values. Now we just need to do a calculation of the relative luminance. How do we do that? There's an easy way and there's a more difficult way. The easy way is very simple, right? You just take the average of the RGB values. So the L value, the luminance value, is basically red divided by 3, green divided by 3, and blue divided by 3. Alpha, you don't care, really. You just take the same alpha. Of course, that's the basic formula. There are other standards. In fact, there are standards that exist. There's one that's ITU RBT.709. That's a version of a standard that gives a particular formula, which you notice that it's not exactly R divided by 3 plus G divided by 3 plus V divided by 3. It's a particular ratio, right? You see G here seems to be particularly higher than the rest. If you do this, then you will actually get a better picture. But I'll show you the picture later on, and you can tell me whether you think this is better or not. So let's take a look at the code. Quite straightforward again. First thing you need to do is you need to create a grid, gray image, right? That's the grayscale grid. It's a new grid that we want to create. And once you've done that, again, we iterate X and Y. And then for each one of them, we first find the color. Pix becomes the color. Remember, this is a color, you need to type assert it into color.nrgba. Then with that, you divide by 3, divide by 3, and divide by 3. Once you have that gray pixel value, you create a new color.nrgba with the same. So this RGBA, so you just put gray, 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 and then alpha, we just use the same alpha. Okay, and that you insert into gray image. Once you've done that, you return it and you save it, you will get the grayscale image, right? So this is the original. The one on the left is original. The one on the right is average formula, the one that divides by 3, right? So this is the simplest method, just divide by 3. And this uses the ITU-RBT 7.09 formula. My personal opinion, the one in the middle actually looks better. But of course, the average formula is a lot faster. Yeah. So whichever you think is the best. So this is converting a color image into grayscale using the Go standard library. Okay, and so finally, I want to talk about how you can resize an image. So resizing a raster image literally means you create an image with a higher number of pixels or a lower number of pixels, right? Because you just either blow up the image or reduce the image. And there are a lot of algorithms. I wouldn't even start talking about it. There are a lot of algorithms. Some are pretty complex. They have very complicated mathematics, but they're all obviously a simple algorithm as well. The simplest one is called the nearest neighbor interpolation. Basically, you're guessing the best color based on the nearest neighbor. Yeah, and how does it work? I'll talk about it in a bit. So the nearest neighbor interpolation is the simplest, one of the simplest. I think it is the simplest and the fastest. But it does introduce jaggedness, right? So you cannot have it both ways. The quality is not as good, but you can actually implement this really quickly. If you're interested in any of the other implementations, feel free to just take a look at some of the algorithms and try to implement it. But for this presentation, I will go with the nearest neighbor interpolation. And what's the algorithm? The algorithm is quite straightforward. So first of all, we assume that we have the original image, right? The image that we have, and how much do we want to scale? So do we want to enlarge it 2 times, 5 times, 10 times, or do we want to shrink it like half, into half, into 1/4, into 1/10, or whichever it is? We know how much we want to scale. So first of all, we create an image with a new size. Then for each pixel in the new image, we divide the X and Y positions with the scale to get X prime and Y prime positions. Okay. Of course, the X prime and Y prime are not going to be whole numbers most of the time. So we find a floor of X prime and Y prime, right? And with this, then you can use X prime and Y prime to map to the original image, and you take that image and you use that to apply the pixel in the image. Okay, so that's it really. That's the nearest neighbor interpolation. Name sounds fanciful, but that's really that's all there is to it. Let's take a look at the code. So here again, the first part here is to create a new grid with the new size. So let's say you want to double the image, then basically the scale becomes 2.0, and then you create a new image here. This is a new grid. Resize is the new grid. Then you loop, and then you find the X divided by the scale, Y by the scale, and you find the floor. And then you take X prime and Y prime, and you map it back to the original grid that you have, and then you put it into the new grid, the new resize image, and that's it. You have your new image. Then you go back, you save, and then you have that new image. Just show you how it looks like. So this is the original image. The one on the left is original image. The one in the middle is a smaller image. I think that's like 1/5 of the size. And the one on the right is the larger image. Now you look carefully, the quality of the larger image and the smaller image are actually not that great. And that's because, the algorithm is simple. It's relatively fast and it's easy to implement, but the quality is not the best. So if you want something better, then you have to pick up the maths and do the implementation, right? But if you just want something quick and easy, this is what it is. Okay, so I quickly ran through a few algorithms on how you do some level of image processing. Straightforward, very simple, straightforward image processing. You can do a lot more, actually. You can do some translation, you can do some rotation. It's mathematics. You figure out the mathematics, and you probably have learned it in your computer graphics module in the university. Pick up some of the books, see how you want to implement it, and it's not that difficult. The performance of the image processing early on, it's not the top most, and that's because I chose to implement it the most straightforward way possible, right? Actually, you can make it a lot faster, and there are many different ways of making it faster. I think the most straightforward one is probably to use concurrency. You do multiple things at the same time, and you let go do what Go does best, right? Which is concurrency, and you can see the improvement. So it can be a lot faster. But obviously, what I want to show here is the simple algorithms so that you can see how easy it is to do image processing in just the Go standard library. Okay, so that's all I have today. Please visit this website and you can get more materials. In fact, you can get an entire article of what I just talked about here, talking to what I just mentioned earlier on in the presentation and some of the new things as well. So that's it for my presentation. Thank you very much.
Right. So Sheong, I imagine this can also be used for simple animation.
Yeah, you can actually do a lot of things. You can do simple animation with this, obviously. And animation is, if you do it like, I don't know how many people used to do that when you're a kid, right? Basically, you draw a picture, and then you draw another picture, and draw another picture. You have 1,000 of them, and you just flip them through very quickly. That's animation, yeah. Mm-hmm. And you can generate your images the same way, and use code to just show them one at a time really quickly, yeah, and you get your animation. And in the middle, then you can do the image processing. If you want to enlarge, you can show like an image slowly becoming bigger and bigger. So what you can do is just pick the base image, make it bigger, and then you show it again. And as you show it very quickly, you can see something sort of like enlarging and so on and so forth.
Okay. There's one question actually from Suyin. Why would you use Go versus a dedicated image manipulation package? Okay.
So there are Go image packages. You can use that. But obviously, if you are writing some code in Go and you want to continue that in Go, then you want to use a package in Go, right? But let's say you don't even want to use another package, then you can just go with standard library. Providing the image processing that you're trying to do is relatively straightforward. So obviously, Go can do a lot more complex ones, but that really means that you need to implement a lot more, right? I'm just trying to show that if your intention is to do something small, then you can just go with a Go package. You want to do a lot more performant ones and so on, then maybe you might want to consider something else. But yeah, let's say you want to use image magic or you want to use something else. You can, but then that's outside of Go, right? So you need to call image magic. First of all, you need to install image magic, and installing image magic is a little nightmare by itself. After you install it, and then you need to call it and you run it, make sure it works, and then you bring back the image and stuff like that. I think that's not really worth the trouble. If you're doing something simple, just use Go